Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss about one number which is called Damkholer number. It has got many importance in the area of chemical reaction engineering. A simple definition of the Damkholer number is dA, it is represented by the term dA, time of flow divided by time of reaction. Okay, this is what the Damkholer number is. It is the ratio of time of flow divided by time of reaction, and it is generally formed by the multiplication of K into tau. K is the reaction rate constant, which is the first order, and tau is the space time. Okay, the units of rate constant is 1 by time. The units of tau is time, and if you multiply K into tau, you get the Damkholer number, the time of flow by time of reaction. If the Damkholer number is higher, the conversion in the reactor is higher. If the Damkholer number is lower, conversion in the reactor is lower. Why? Because Damkholer number higher means time of flow is higher than time of reaction. That means you are allowing more time to react, because divided by time of reaction. Time of reaction is minimum time that is required to reaction to occur. Time of flow means how much time a reactant is spending inside the reactor. If it spends more time than it is required for the reaction, of course the Damkholer number will be higher, the conversion will be higher. If you are not providing sufficient time in the reactor, that means you are keeping higher flow, that means most of the reactants trying to come early from the reactor. It won't spend most of the time here. If it won't spend most of the time, then the time required for necessary conversion, the denominator value, it will be higher than the numerator value. That means if a feed, okay, of reactants is spending more time in the reactor, that means the Damkholer number is higher. That means more conversion is possible. If a reactant is spending less time in the reactor than it is required time, then what happens? Of course the conversion will be down. So that is what the importance of the Damkholer number. And second is, if you want to compare two reactors of different size, example, I have one CSTR of 2 liter, one CSTR of 10 liters, how I can compare these two? If small reactor and big reactor have the same Damkholer number, then the conversion in the small reactor and conversion in the big reactor will be the same. That is what the very simple application of Damkholer number. Let us do that. That means if the smaller reactor which is having the Damkholer number of example 0.05 and bigger reactor which is having a Damkholer number of 0.05, then in both the reactors the conversion will be same. Let us do that. Let us proceed for that derivation. This is my reactor. I am talking about the first order system now. Okay? And the liquid phase reaction is happening in the reactor, and example. Okay? And the inlet is Fa0, Ca0, V, nu 0, outlet is Fa, Ca and nu. Molar flow rate, concentration and volumetric flow rate. This is a exit molar flow rate, exit concentration, exit volumetric flow rate. If it is liquid phase reaction, there is no change in the volumetric flow rates, then exit volumetric flow rate is equal to inlet volumetric flow rate. Imagine a first order reaction is happening in this reactor. We know the design equation. Volume of the CSTR is equal to Fa0 by minus Fa by minus Ra. Minus Ra is the rate of reaction. Here we have taken first order. So minus Ra is nothing but K into Ca. If you my flow rate, flow rate is nothing but concentration into volumetric flow rate. Now you replace Fa0 with Ca0 and nu 0 and Fa with Ca in nu. Okay, this Fa is nothing but Ca into nu is equal to Fa. So if you substitute these two in this equation number 1, you get volume is equal to volumetric flow rate into Ca0 minus Ca by Kca. Take this to the denominator, and V by nu 0, which is volume by volumetric flow rate, is nothing but space time, that is amount of time that is spending in the reactor, Ca 0 minus Ca by Kca. If you take out the concentration on one side and rest every terms on the other side, you get Ca is equal to Ca 0 by 1 plus tau in, that means exit concentration is equal to inlet concentration divided by 1 plus space time into reaction rate constant. Now this tau k, what we have discussed here is nothing but the Damkholer number. Okay. Now Ca by Ca 0 nothing but 1 by 1 plus Damkholer number. I know x is equal to, conversion is equal to initial concentration minus final concentration divided by initial concentration. From that, Ca by Ca 0 is equal to 1 minus x. Therefore, x is equal to, if you substitute in place of Ca by Ca 0 and equation number 5, then what happens? X is equal to the conversion in this reactor is 1 minus 1 by 1 plus Damkholer number. That means if you know the Damkholer number of a reactor, you can estimate what is the conversion in that particular reactor. So using this formula, I have already explained, if higher is the Damkholer number, higher is the conversion, lower is the Damkholer number, lower is the conversion. That's what I have given example. I have substituted different Damkholer number values. For a Damkholer number of 0.1, what is the conversion using this equation is 9%. For the Damkholer number of 0.5, 33%. For a Damkholer number of 1.5, it is 60%. Okay? That means if you increase the Damkholer number, conversion increases. If you decrease the Damkholer number, the conversion decreases. Now let us apply the fundamental of the Damkholer number to the two reactors. One reactor is small, another reactor is big. Even though one is small, the another one is big, as long as the two reactors having same Damkholer number, the conversion in this reactor is the same, the conversion in this reactor the same, whatever may be the values of the volumes or volumetric flow rates or rate constant. For example, this is S represents, I am talking about the small reactor, the L representing I am talking about the large reactor. So the volume of the small reactor is 2 liter. The rate constant, that means of a reaction which is happening in this reactor, is 0.1 per minute, and volumetric flow rate in this reactor is 4 liter per minute. Here it is different. The volume is 10 liter and the rate constant for the large reactor is 0.01 per minute and volumetric flow rate is 2 liter per minute. Both are different values. Let us see what happens at the final stage. Now, for me to use this particular equation, I have to find out what is Damkholer number. Damkholer number nothing but space time of the small reactor into reaction rate constant for the small reactor. Okay, let me come this side. Now, I know space time is equal to volume by volumetric flow rate, which is 0.5. Rate constant is already given 0.1 per minute. From this, Damkholer number is equal to 0.5. If I know the Damkholer number, I can use equation number 6 to estimate what is the conversion in this small reactor. 1 minus 1 by 1 plus Damkholer number small. The conversion is 0.047, that means 4.7%. That means given this Damkholer number of 0.05, the conversion in this reactor, whatever may be the initial concentration, whatever may be the final concentration, example, for a given initial concentration, always the conversion will be 4.7. Okay. Let us take the example of this. I know Damkholer number for the large reactor. Okay. Let us calculate what is the space time for the large reactor, volume by volumetric flow rate, which is 5. The Damkholer number is space time of the large reactor into rate constant in the large reactor. If I do that, my Damkholer number is 0.5. From that, the conversion using this equation is 0.047, which is nothing but 4.7%. Imagine these values are different, these values are different. Still, The conversion here is 4.7%. The conversion is 4.7% because the Damkholer number of this reactor and Damkholer number of this reactor is the same, which is 0.05. Now you can compare the efficiencies of the reactors, which one is best. That means if you know the Damkholer number of this reactor and Damkholer number of this reactor, straight away you can say that which one is the best, without going into what are the volumetric flow rates, what are the concentration. It is simple enough. And because there are many textbooks which comes with the Damkholer numbers, straight away look into the Damkholer number and Damkholer number of the other reactors, okay, and see which one is higher among the two reactors, whether it is small or big, which one is having a higher Damkholer number, the conversion will be more in the Damkholer number, I mean in that particular reactor. I hope you understand the simplicity of the Damkholer number. Okay, let us meet with the new lecture. Thank you.